The Red Book structure mandates a very strict division of liability.
So the employer or the entity funding the project, they just dictate the design, right?
Exactly, but the contractor is the one who actually executes it. The contractor absorbs the extreme risk of the temporary works, safety failures, and just exact, down to the millimeter physical compliance.
Which means this scope of work is basically the genetic sequence of a massive facility. Every single variable, from the deepest foundation to the highest fence, has to be sequenced and priced perfectly on paper before a single shovel even hits the dirt.
It's all about control, complete control before the chaos of construction starts.
Right, and we're going to decode how this document forces a contractor to manipulate fluid dynamics, navigate the extreme chemistry of concrete, and manage just a weaponized level of paperwork to keep a multi-million-euro project from devolving into total ruin.
Because the physical transformation required to execute a design like this is, well, it's staggering. Before they can even think about building up, the contractor has to aggressively neutralize whatever is currently occupying the site.
The scale of the demolition in the early pages is surgical, but also kind of violent. We aren't talking about knocking over an old shed.
No, not at all.
The contract specifically accounts for cutting down massive ancient trees. We're talking up to 5 meters in girth. And they have to excavate and rip out existing underground pipelines up to 500 millimeters wide.
And it's not just pulling out old pipes. They are legally bound to bring in licensed specialists to handle the extraction of asbestos, lead paint, and contaminated soils.
So it's basically a hazmat operation before it's a construction site.
Exactly. And once the site is stripped bare of the past, you're left with the geology. And when you look closely at the earthworks requirements here, you quickly realize that digging a massive hole is almost never a battle against dirt.
It's a war against water, right? Like hydrogeology.
Yes. The dewatering systems detailed in this contract completely upend how most people think about excavation.
Okay, let's unpack this. Because I assumed if you dug a deep trench and hit water, you just, I don't know, dropped a pump in the puddle and routed it away.
A lot of people think that. But this document mandates highly engineered preventative dewatering systems. The contractor has to install shallow systems for water reduction up to 1,000 millimeters using well point headers spaced exactly at 1,500 millimeter centers.
And for the deep systems, anything over 1,000 millimeters, those well points have to be placed every 1,000 millimeters.
Right. And to understand the mechanics of this, you really have to picture the water table. The ground beneath us is often fully saturated.
Like a sponge.
Exactly. So if you dig a 10-meter hole in saturated soil, the surrounding earth will instantly bleed water into your excavation, turning the dirt walls into, well, liquid soup.
And that just collapses under its own weight.
Completely. So by driving these well point headers deep into the perimeter of the site and connecting them to massive vacuum pumps, they're temporarily altering the local geology.
Wow. So they're creating a localized, completely dry crater by aggressively sucking the groundwater away before it can even reach the excavation walls.
Yeah, you are artificially pausing the natural flow of groundwater so your heavy machinery doesn't sink into the earth. It's an incredible manipulation of the environment.
That's wild. And right alongside those extreme measures, like they mentioned drilling and blasting solid rock more than 15 meters deep, you have these microscopic environmental requirements.
The contrast is pretty amazing.
It really is.
Oh.
And that brings up a detail in section 5.9 that completely caught me off guard. After detailing heavy explosives and deep well vacuums, the document suddenly mandates the installation of silt sausages and core fiber mats.
Silt sausages, always a fun term.
Right. I was like, wait, does a contractor managing a mega project really need to micromanage mud puddles with something called a silt sausage?
They do, because a cleared construction site of this magnitude is essentially an enormous ecological wound.
Oh, that's a good way to put it.
When you strip away the vegetation and expose thousands of tons of loose topsoil, a heavy rainstorm will turn that site into a massive sediment factory.
And that sediment would just wash directly into the local rivers or, municipal drainage systems.
Exactly. Choking out aquatic life and destroying the local watershed. So these silt sausages, which are basically long, heavy geotextile tubes filled with sand or compost, they act as miniature check dams.
So when you combine them with the core fiber mats and the jute mesh, they create a site-wide filtration system.
Right. The water is allowed to leave the site, but the suspended mud and silt are physically trapped behind the fabric.
It's not just a nice thing to do, it's a legally mandated preventative measure.
Oh, absolutely. If a contractor fails to filter their runoff, they don't just get a fine. The entire project can be shut down by environmental regulators.
Okay, so the geology is paused, the site is this perfectly dry, heavily fortified crater, and the mud is physically trapped. Now, they have to actually anchor the structure.
This is where the physics of the materials take over.
Right. Before they pour any standard foundations, they're constructing diaphragm walls and cast-in-place concrete piles under what the contract calls bentonite support.
Which is such a fascinating process.
When I looked into the mechanics of this, I was honestly amazed. It is essentially liquid shoring.
Yeah, it's one of the most elegant engineering solutions in heavy civil construction. Think about when you need to drill a massive cylindrical shaft deep into loose sand to pour a concrete tiller.
The walls of that shaft just want to cave in the second the drill bit is removed, right?
Exactly. But they can't just drop steel casings all the way down every single time. It's too expensive and impractical. So instead, as they drill, they flood the hole with a bentonite slurry.
And bentonite is like a highly absorbent clay, right?
Yes. When you mix it with water, it hydrates and expands, creating this incredibly dense, heavy, viscous fluid.
And the physics of that fluid are the key here, because the bentonite slurry is significantly heavier and denser than the surrounding groundwater and loose soil.
So it exerts a massive outward hydrostatic pressure against the dirt walls of the shaft. It literally physically holds the loose earth back.
That is so cool. And then they lower a massive steel rebar cage directly into this pool of clay.
Right into the liquid.
And when they're ready to pour the concrete, they pump it straight into the bottom of the shaft through a specialized pipe called a tremie.
And because wet concrete is even heavier and denser than the bentonite, it pushes the clay slurry up and out of the shaft as the concrete rises.
So it replaces it perfectly without the dirt ever having a chance to collapse.
You're balancing the specific gravity of 3 different materials, soil, clay slurry, and wet concrete, in real time, deep underground.
It's just a crazy juggling act. And the stakes for getting this right are laid out explicitly in the pile testing requirements.
Which goes back to your Boeing 747 analogy.
Exactly. The contract legally requires the contractor to run maintained load tests on these newly cast underground concrete pillars. They have to push them to bear 800 to 1,000 tons of force.
They use these massive hydraulic jacks to press down on the pile, and they're measuring the settlement down to the fraction of a millimeter.
And if that concrete pillar sinks or cracks under that pressure, it means like the bentonite mix was wrong or the concrete didn't cure correctly.
And that pillar is essentially useless. You have to start over.
To survive that level of extreme force, the contractor is working with a highly complex menu of concrete classes. The document lists everything ranging from Class 15 all the way up to Class 60.
And they're incorporating massive precast structural elements, too. We're talking about craning and roof slabs and structural beams weighing up to 20 tons each.
But the reinforcement methods have evolved far beyond just tying heavy steel rebar together, haven't they?
Oh, massively. The document specifies the use of fibrillated polypropylene fibers and CFRP, which is carbon fiber reinforced polymer strips.
This feels like a major shift in how we build, because traditional steel rebar is fantastic for tensile strength, right? Like it stops the concrete from snapping when it bends.
It does, but steel has a fatal flaw. If water penetrates the concrete, the steel rusts, it expands, and it literally blows the concrete apart from the inside.
Spalling, I think they call it.
Exactly. So by weaving CFRP strips and synthetic polypropylene fibers directly into the structural elements, you're introducing massive tensile strength without the vulnerability of rust.
It's incredibly lightweight compared to steel, but vastly more durable in a corrosive underground environment.
Right. Now that you have these incredibly dense 1,000-ton tested foundations in place, you have to weave the facility's lifelines through the earth before the final concrete slabs are poured.
The sheer volume of material that gets buried forever is astonishing. The contract details laying down underground pipelines with a nominal bore of up to 1,200 millimeters.
That's nearly 4 feet wide.
Next time you walk across a paved lot, think about the maze of glass fiber and 4-foot-wide epoxy pipes right beneath your shoes.
It really puts it in perspective. And you aren't just burying standard PVC. The contractor is managing glass-reinforced epoxy, or GRE pipes, high-density polyethylene, and galvanized carbon steel.
The choice to use GRE pipes for specific systems is super fascinating to me. Unlike galvanized steel, which relies on a zinc coating to fight off corrosion, glass-reinforced epoxy is inherently immune to rust.
Right. Inherently immune and highly resistant to aggressive chemicals. If they are routing caustic industrial waste or highly saline groundwater, a steel pipe would eventually degrade.
So GRE gives them a lightweight, chemically inert pipeline.
Precisely. And right alongside those massive 4-foot chemical and water veins, they are pulling the facility's nervous system.
The cabling.
Yeah, the document outlines a massive spectrum of cabling. You have these huge, high-voltage single-core cables up to 240 square millimeters thick, carrying huge amounts of raw power.
And running practically parallel to them, you have incredibly delicate fiber optic bundles, the FO96 cables, and specialized gas detection wires.
And the proximity of all these systems underground is exactly why Section 9.2 is so uncompromising.
Right. It dictates that absolutely all pipelines must undergo rigorous hydrostatic pressure testing before the contractor is allowed to backfill the trenches with dirt.
Because the weak link in an underground pipeline is almost never the pipe itself. It's the fittings.
The blind flanges, the reducing T's, the elbows.
Exactly. The contract demands that every single fitting perfectly matches the pressure rating of the parent pipe.
Because if a contractor tries to save, a few thousand euros by utilizing a cheaper, lower-rated reducing T on a massive high-pressure GRE line.
That fitting becomes a ticking time bomb.
Yeah.
If it blows out 3 years later, under 3 meters of compacted earth and a foot of reinforced Class 60 concrete, the cost to excavate and repair that single failed joint is astronomical.
So the pressure test ensures the integrity of the physics before the dirt hides the evidence.
Exactly.
Which brings us to the operational reality of managing all of this. We've decoded the deep dewatering, the bentonite fluid dynamics, the fiber optics. But how does a contractor actually coordinate thousands of moving parts without the site collapsing into total chaos?
Well, they manage the chaos through an utterly weaponized level of paperwork.
I love that phrase. Weaponized paperwork.
It's true. The entire site is governed by the Inspection and Test Plan, or the ITP.
Sections 17 and 19 detail this plan. The ITP establishes 3 rigid classifications for every single physical action on the site.
Yeah.
Review points, witness points, and hold points.
A review point is pretty straightforward documentation, but a witness point requires an inspector to physically stand there and observe a test.
Like the Marshall test for asphalt every 500 square meters.
Yes.
The Marshall test is brilliant. An inspector literally watches them extract a coarse sample of the freshly laid asphalt, and then they place that sample into a machine that crushes it.
They're measuring the exact flow and stability of the pavement under extreme compression.
If the asphalt deforms too easily, the contractor isn't allowed to pave the next section.
And then you have the slump tests for every single concrete delivery.
Right, taking a fresh batch of concrete from the truck, filling a standardized metal cone, lifting the cone away, and measuring exactly how many inches the wet concrete sags or, slumps.
It is a low-tech, immediate way to verify the water-to-cement ratio.
If the concrete slumps too much, it means there's too much water in the mix, which permanently compromises the curing strength. The inspector watches the slump, and if it fails, that truck is rejected and just sent away.
But the ultimate enforcement tool is the hold point.
I look at a hold point as a strict legal quarantine. Like a video game boss battle, you absolutely cannot bypass to get to the next level.
That's a great way to think about it. 100% of the piles require an integrity test, and it is classified as a hold point.
The contractor literally has to drop their tools and halt all forward progress on that section of the site until the employer's engineer physically signs off on the test results.
Liability instantly shifts, and no one moves until the paperwork is cleared.
It's rigorous, but obviously it's necessary.
Yeah.
But here's where I genuinely struggle with the logic of this document. Time is the single most expensive commodity on a mega project.
Oh, an idle site bleeds money.
Right. Yet Section 19 demands that the contractors submit method statements and concrete mix designs a full 28 days before they intend to start the work.
Yeah.
Even a simple rebar bending schedule requires 14 days' notice.
It is a massive built-in delay.
How does modern construction companies survive waiting a month for an engineer to rubber stamp a chemistry equation?
It sounds financially paralyzing, I know, but you have to view that 28-day window through the lens of a FIDIC Red Book contract.
Okay, how so?
Well, the employer designed the structure, but the contractor guarantees the execution. Once you pump 50 cubic meters of Class 60 concrete into a trench full of bentonite slurry and that concrete cures.
It's literally set in stone.
Exactly. If the contractor pours that concrete and 28 days later the cylinder crush tests reveal that the mix design didn't meet the required compressive strength, you have a monumental engineering disaster.
Because you can't unpour concrete.
No, you can't. You have to bring in heavy machinery and demolish your own newly built foundation.
Ouch. So that 28-day submittal window isn't just bureaucratic red tape. It's the time required for structural engineers to intensely audit the chemistry, verify the aggregate sourcing, and validate all the math.
The paperwork is the safety net for the physics. On a project of this scale, the paperwork is the absolute only way to verify the structural integrity of materials that are about to be buried in the earth forever.
Wow. And the legal hooks remain embedded in the project long after the heavy machinery leaves, too.
Section 22.
Yeah. Section 22 details the defects notification period, the DNP. Even after the facility is completely finished, cleaned up, and officially handed over to the employer, the contractor is legally bound to remain available to attend the site within 48 hours of any defect notification.
You cannot just hand over the keys and dissolve the LLC.
Right. You are financially chained to the physical reality of that structure for the entire duration of the DNP.
If a high-voltage cable shorts out or a GRE pipe flange leaks, your crews are back on that site in 48 hours, fixing it on your own dime.
We started this deep dive looking at construction as just, noise, dust, and chain link fences. But by decoding this single 15-page FIDI scope of work, we've really exposed the invisible architecture that actually builds the world.
We've seen how engineers use massive vacuums to temporarily pause hydrogeology.
And how they utilize bentonite clay to manipulate fluid dynamics deep underground.
We've examined the shift from heavy steel rebar to incredibly strong carbon fiber polymers, and we've mapped a nervous system of 4-foot-wide epoxy pipes and delicate fiber optics.
And we navigated the intense operational algorithm of Marshall asphalt crushing, concrete slump tests, and strict legal quarantines that force a contractor to perfectly sequence the physical world.
It is an extraordinary process. It transforms chaotic raw materials into a safe, durable piece of civilization.
It really does.
But, it leaves you with a final, fascinating tension to consider.
What's that?
Well, a document like this, FADISOW, is a marvel of human control. It attempts to perfectly quantify, price, and legally bind the physical world down to the millimeter. But nature is fiercely unpredictable. If the contractor is excavating and hits an entirely uncharted underground river, or if an unseasonable 100-year flood washes over those perfectly engineered silt sausages.
Oh, man.
How does a rigid, euro-denominated legal text bend without breaking? It invites you to ponder what happens when perfect legal theory ultimately collides with a messy, uncontrollable physical reality.
That is a brilliant point. The DNA on the paper might be flawless, but the environment always gets the final say. Next time you walk past a massive excavation site, just imagine the invisible forces, both the hydrogeology and the paperwork, holding those dirt walls back. Thanks for joining us, and we'll catch you on the next deep dive.
See the link in the description for free PDF download. Also, watch our other construction scope videos. Thanks for watching. Please subscribe and see you next time.